guest faculty, Professor Gautami Bhomik, will talk about the Riemann hypothesis. Sorry, her lecture, the first lecture begins, and it will be a continue. So yesterday we finished with the proof of the prime number theorem, and today she takes over on, and her first lecture is about the Riemann hypothesis. Thank you.
And the Lindelof hypothesis. Both of these were mentioned in the first talk. You remember this? That Ritobuto Munshi spoke about these two, and probably you've heard this word like Riemann hypothesis, even if you haven't heard the Lindelof hypothesis. It's probably one of the best known open problems, at least in number theory. And probably if you can solve it, you get something like $1 million. But I think if you solve it, you will not need the $1 million. So, so what is it? What is this Riemann hypothesis? It's so it's a very simple statement. I mean, that's since the statement is so simple, it looks as if the proof also should have been simple. Somehow this is not, and this is it's getting to be old now. It was in 1859 that this it dates to 1859, where, as far as we believe, Riemann never thought of this as being a very difficult problem. Somewhere, I think in a note, he said that he hadn't completed the proof or something of that kind. You know, it's like Goldbach, of course, much later, that probably he believed it was much, we believe he believed it was much simpler than it is. I think that's a somehow somewhat safe assumption to make. So what does it say? It says, now you saw in the previous classes that the Riemann Zeta function was defined, and we did several things on them. And you also saw something about the zeros. You saw that there are trivial zeros and there are non-trivial zeros. We know that there are infinitely many trivial zeros, which you know where they are. They are on the negative even integers, and we don't really care about them. I mean, they are simple and trivial, and we know what to do with them. The others are non-trivial. These are complex zeros. We know that there are infinitely many complex zeros. This is known. Okay, so how we can now, in modern language, state the Riemann hypothesis is that all non is this kind of writing okay for people who may be looking at it from far away? Is it, can they read? That's okay. Okay, so all non-trivial zeros of the Riemann zeta function lie on the line S is equal to half. Okay, so let's say sigma is equal to half. Yeah. So because by convention we are going to use, for complex numbers S is equal to sigma plus I tau. Did you use the same tau, or did you used T? Okay, that was conventionally used, sigma plus IT, and therefore many people continue to use sigma plus IT. I don't know, if it doesn't bother you, I can write sigma plus I tau, because then, I mean, it's somehow more consistent to have sigma and tau both being Greek letters. And so sigma is the real part, and so this is believed that the zeros will be on this line. So what is known here is what are very classical results, and are known are Hardy, who very long ago, in 1914, he proved that zeta s has, so the Riemann zeta function, we are using the notation like always, zeta of s is equal to sum of 1 n to the power s, n is equal to 1 to infinity, and s is a complex number. Okay, we take care of its convergence and so on. So zeta s has infinitely many, this is known, zeros on the critical line. This is the critical line, yeah? Sigma is equal to half. Yeah. So here we are, half here and 1 here. Yeah. So things behave, as you saw before, things behave pretty nicely here. Okay, this is the critical line. And then we have the critical strip here. So, so already Hardy proved this in 1914, and Selberg in 1942, he proved that a positive proportion, these are very classical kind of results. You know, when you can't show something exactly, you at least try to show that there is a positive proportion. Yeah, a positive proportion of zeros. And when I say zeros, I mean complex zeros, non-trivial zeros, are located on the critical line. What does this mean? What do I mean by the statement positive proportion? By positive proportion, I can state this in a more refined language, in a more mathematical language. So if supposing I write n of, I can use some notations. I don't know whether we wrote them already or not. So notations are, we are going to use n of for the number of zeros. Okay, so these are conventions, and these are notations. So yeah, let n of t, by n of t, I denote the number of zeros, which I denote by rho, where yeah, I must tell you one more thing. Gamma is between 0 and t. Yeah. So so what is rho? So rho is a non-trivial zero of the Riemann zeta function. Yeah. And often we write rho is equal to beta plus I gamma. Okay. At least for today, let's do this. If you don't like the notation, somehow we can change it. Maybe this afternoon we can change it. But so where am I? Here am I. Here is my imaginary part. This imaginary part is somewhere between 0 and t. Yeah. So somewhere here. So some t, some fixed t. So you construct a rectangle here, and then it's in this rectangle. Yeah. Some kind of a rectangle here, and it is in this rectangle. So these are all the zeros, n of t. And now you are interested in n0t. So n0t is the number of tau This is the cardinality of this set where tau is between 0 and capital T, and zeta of half plus I tau is equal to 0. Yeah. So what Selberg proved was that Selberg, if you want to to write this in mathematical language in terms of nt and n0t, so Selberg proved, I said that a positive proportion of zeros are located on the critical line, which means that if I divide nt by n0t by nt, then this is greater than or equal to some constant, some positive constant, c a positive constant. Okay. So, and t is large. So this means that there is a positive, which is better than that is Hardy's result, where he says that there are infinitely many zeros. Yeah. So what we know, I think what you have already seen that that the Riemann zeta functions has no zeros in the half plane sigma greater than 1. You have seen this, yeah? So here there are no zeros. I know that. There are no zeros here. Yeah. These are facts. So we won't fight about these things. We will believe, we have seen that these are true facts. Zeta of S has no zeros in the half plane sigma greater than or equal to 1. There's no problem here. You don't have to worry about this. Okay. So, so in fact, the Riemann hypothesis, if it is true, would mean that n0t is actually equal to n of t. Yeah. So that is what we would like to show. Is this true? Yeah. So I want to talk to you about the functional equation, which you haven't seen yet. Yeah, I'm not going to go into detail on the functional equation. Since you have a weekend, I'm going to give you a lot of difficult questions, which you'll study all in this weekend. Whereas I am going to visit all sorts of places, but you will study. So, and for those of you who are new and who do not know, not the seasoned ones. So yeah, these we believe. And then now I want to talk to you about the functional equation. There is a misconception somehow that a functional equation has to be always in S and 1 minus S. Nothing's, it's just that it happens that there is a symmetry in S and 1 minus S. Yeah, it could have been something else, and you can have functional equations in other forms as well. But what it means is there is a symmetry. Yeah. So so let me write the functional equation. This is the functional equation. For those of you who have not seen it, well, here it goes. So zeta of S is equal to 2 to the power S. S is always my complex number, pi S minus 1 sine of pi S by 2. This is the Euler gamma function, 1 minus S and zeta 1 minus S. So there is zeta 1 minus s here and zeta s here. After that, there are some other things here which we know, and therefore we could write it in a simpler form if we wanted to, so in a more symmetric form. So what do we not know here? Do you know the Euler gamma function? You know the Euler gamma function? Okay, first let me write this in a nicer way. So so I can write this as zeta s in a more symmetric form. I can write this as zeta of s is equal to, I put in the rest of the stuff here, chi of s zeta 1 minus s. Yeah, and what is chi of s? Chi of s is equal to 2 to the power pi s minus 1 gamma 1 minus s sine pi s by 2. Have I got everything correct? There's another 2 because it's 2 to the power s. So 2 to the, yeah. Okay, so what is this gamma? Do you remember what gamma is? Have you seen, in the first talk you talked about, I think you did some of these exercises with them. So yeah, so this is the, I can repeat a bit. There's no harm in repeating. I mean, if you find that I'm going too slowly, please tell me. I can speed up. But if you, it's better that I go a little slower than I go too fast, and that you feel very sad at the end of the day. That's not a good idea. So here we are. So these are very, very classical functions. Yeah. So this is called the Euler gamma function. Yeah. So from the 18th century, 1729, and it's you could define it in several equivalent ways. So gamma of s is equal to 1 by s, 1 plus 1 by n to the power s, and 1 plus s by n, where s should not be 0 or minus 1 or minus 2 or etc. Yeah. So and the product, there's a product, and the product converges uniformly on any compact set of the complex numbers if you remove the negative numbers from them, negative n from it. Yeah. But there's another way of writing this gamma of s, which you may be more familiar with. It's written as an integral so gamma of s, which is the same thing, is equal to an integral 0 to infinity of t to the power s minus 1 exponential minus t dt. And if you write gamma n of s as ns by s, ns into factorial n, s into s minus 1, etc., by s minus n, and you let the limit of, and you take the limit as n tends to infinity of gamma n of s, then you get gamma of s. So let's say you do this as the first exercise. Okay, so show that these two are actually the same. Yeah, these two definitions. Euler showed that these were the same. So this is 1 and this is 2, this is 3. Yeah, and show that 1, 2, and 3 are equivalent. I mean, it's pretty easy, yeah, but just convince yourself that this happens. And then there is a, yeah, are things okay till now? Is there anything that's, so, so that's the gamma. This is the Euler gamma function that's here. Yeah, that's the Euler gamma function that's here. And so you know everything. You know pi, you know sine, and you know, so zeta, how to express zeta in terms of zeta s in terms of zeta 1 minus s. Yeah. So this is the functional equation. And yeah, there's one more thing you might like to, yeah, I'll give you a hint here. Yeah. So um, a property that you might use, which is called the duplication formula, which is due to Legendre. So for the Euler gamma function, so this says that gamma x by 2 and gamma x plus 1 by 2, this is equal to square root of pi 2 to the power 1 minus x gamma of x, yeah, for x positive. You might like to use this when you are working with gamma. Okay, so now I want to, since I said the Riemann hypothesis, and since, as you can very well imagine, I'm not going to prove the Riemann hypothesis, maybe you will in some years. So, and then you must thank us for having organized this course, because that's the first time you saw the Riemann hypothesis. There are in the first talk, you heard about the Lindelof hypothesis as well. You also heard that the Lindelof hypothesis is weaker than the Riemann hypothesis, however, expected to be more difficult. I don't quite know. I don't have a good enough intuition on the question why Lindelof hypothesis is more difficult than the Riemann hypothesis. I haven't worked on it myself. So anyway, all this is very much in the realm of fantasy, because probably Riemann hypothesis isn't going to be solved just now, and then Lindelof hypothesis. However, we do know that we can show that what implies what. Yeah, and that's what we are going to do now. So I want to talk to you. I need some definitions. Yeah. So what you also know, where are my facts? Yeah. Yeah. You also know. That when sigma is less, so we said this, zeta s has no zeros in the half plane sigma greater than or equal to 1. And you also know that the order of magnitude 1 the order of magnitude of the zeta function, of the Riemann zeta function on vertical lines is completely known for what? Do you know? For which sigma? So sigma greater than equal to 1, we know there are no zeros. And for sigma, so what's left? Sigma less than 1. Yeah, but you know where the critical strip is. So you have to avoid this critical strip. And then now you are on the left of sigma. So it's sigma less than 0. Yeah. The rest of it is what we don't know so much about. So for this, I'll need a bit of technical, a bit of definitions, which are not that difficult. And so you might have seen these in your complex analysis courses, but doesn't hurt to see it again. So definition is what is or when I have a function. When do I have a function of finite order? Have you seen this a function of finite order? Or if you haven't seen it, let's see it. So, one question in complex analysis that we like is to know how far can a function be continued. You know there are problems somewhere. I mean, a function is not all smooth and nice. I mean, such functions don't exist that much. Yeah. So there is a problem. Where can you have an absolute convergence? And where can it be further continued? These are important questions. Yeah. And then to measure where they can be continued, we need some tools. So these are some of these tools, which, if you have heard, are called the natural boundary. The natural boundary of a function. Can it be continued to the whole complex plane? Zeta S can be continued to the whole complex plane meromorphically. Not all functions can be continued. In fact, a lot of them behave quite badly. Yeah. So I'll define here a function capital F is in a given domain. So in a domain, let's call it D. D is a good name for a domain. Is said to be a finite order the order is finite when a finite order in D, of course, in D, if f of s is less than absolute value of tau to the power a for some positive constant a. Okay, and tau greater than or equal to 1. So are you familiar with this less than concept? So let's repeat what this means. This is the Vinogradov Vinogradov symbol. Yeah, so we assume that we know these. Yeah, we don't need this anymore. We can remove this. So there's a notation. So the two sorts of notations that are used. So you probably know the big O, and you may not know the less than. So the big O is the Landau notation. So this is Landau, and that's the same thing as less than of Vinogradov. Yeah. So what does it mean? It means that there exists some constant. Okay. So both of them, they mean the same thing. There exists a positive constant. Okay. Such that absolute value of f is less than or equal to constant times absolute value of g. The constant c need not be absolute. Okay, it may depend on certain parameters, and if it does, so this c may or may not be absolute. So that's what I mean here. Yeah, that this f of s is less than, there exists a constant a. Yeah, so then it is called a function of finite order. Yeah, and now so do you see what's going to happen if I have a domain of convergence? If a function can be has a if f has a domain of convergence, then it's, if you take any, what will happen? Can you guess what? Can you somehow see what's going to happen? You take anything closed inside that, and then you will get a function of finite order. If you are inside, if your d is uh, is no, yeah, if your d is a sub is something that is inside the absolute, that's just a remark. Yeah, so okay, but I could write it. Remark, in any closed half plane in its domain of convergence, a Dirichlet series yeah has finite order. So this is what I was telling you about, that it might be of great interest to see where there is convergence and how far we can carry it. Yeah, whether it can be carried further or whether we should stop somewhere. And now here, I talked to you about this function of finite order. So here now we are going to come to Lindelof's work on the zeta function. Yeah, I think that one thing is true. Lindelof's hypothesis is less known than the Riemann hypothesis. Yeah, is that true? Did you ever hear, very young people, did you ever hear of the Riemann hypothesis? Yes, but not of the Lindelof hypothesis. Yeah, you didn't hear of it before. So yeah, we believe we can take these notations. And now I want to tell you what the Lindelof hypothesis, what Lindelof really did. So here is a definition. Here's a definition. So now that I know what a function f when it is of finite order, so let f be a function of finite order in some domain D. Yeah. Then I define then the Lindelof mu function is defined as, you remember how we defined finite order. So finite order means the existence of some A for which this big O or the little less than relationship will hold. Yeah, this one. So the Lindelof mu function is this function mu of sigma. Sigma is a real number which depends on this function f sigma, and this is equal to the infimum of all a real numbers such that this condition is true. Yeah, f of s, the absolute value of not absolute value of s, but of tau is tau of a. Yeah, yeah. So this mu has nothing to do with the Mobius mu, which you have seen quite often. Why Lindelof used mu here is something I don't know. But don't confuse the two. The Mobius function mu is defined for integers. Yeah, whereas this one, I mean, they're quite unrelated, this mu and that mu. So it'll be clear from the context when we are talking about the Lindelof mu and Mobius mu. Yeah. Though this afternoon we might be talking, we might be using both of them. Okay. So and now for zeta s, so this is Lindelof mu function. Yeah. So so for zeta of s, Lindelof calculated this mu for a lot of things and then conjectured something. For the Riemann Zeta function, mu of sigma, this is equal to, so you remember that there are two parts that have just gone away from the board, but almost there still. Sigma greater than 1 and equal to 1 and sigma less than 0. These are two parts which we know something about. And so Lindelof worked a lot on these sort of things, and he showed that he came to a guess, which is the Lindelof hypothesis. So this is half minus sigma if sigma is negative or 0, and it is 0 if sigma is greater than 1. Okay. So what happens? What happens? Question. What happens to mu of sigma in the critical strip? Okay, that's the question. That's, I don't know, probably $500,000 question. It's so what happens to mu of sigma in the critical strip? So now sigma is not in this comfortable range of being either less than 0 or greater than 1, but between 0 and 1. Okay, critical strip means sigma is between 0 and 1. Yeah. So Lindelof conjectured that this mu of so what is known as the Lindelof hypothesis there are equivalent forms of this, that mu of sigma, this is the maximum of half minus sigma and 0. That means there are two half lines. Okay, so the maximum of half minus sigma and 0. And this implies that, so by convexity, we can say that mu of half is 0. Okay, so this is a qualitative, uh, you can satisfy yourself that this is true. Yeah. So this, if you look at the definition of what of this finite order functions, then this, look at the definition of mu. Here is the definition of the Lindelof mu function. Then you can also say this. Okay, you can also say this as the Lindelof hypothesis as sigma. So I'm still at the Lindelof hypothesis. Okay, this can also be written as sigma of half plus I tau is less than tau to the power epsilon for all positive epsilon. And here, as I told you, that when you use the Vinogradov or the O big O symbol, we don't know whether the constant is absolute or not. In this case, the constant depends on epsilon. Yeah. So, are there any questions? Is everything okay till now? Any questions? I mean, do the people online ask questions or they don't? Okay, so they know what all this is. Which magnitude? Yeah, so it is the how it's growing. Yeah, that means how it's growing. So I'm going to give a quantitative version, and he can see what we are talking about. Yeah. So so there is a quantitative version. This is so a quantitative version of the Lindelof hypothesis is this quantitative version is when you assume the Riemann hypothesis. Yeah, if you assume the Riemann hypothesis, if the Riemann hypothesis is true, as I told you already, then there exists a constant which is positive. Yeah, a constant C which is positive, such that maybe that's what you wanted to zeta of S, the absolute value of this is less than the C, this C, there exists such a C log tau by log tau. Okay, and this happens uniformly for sigma greater than or equal to half and tau greater than or equal to 1. Okay. So, so I told you that the Riemann hypothesis implies the Lindelof hypothesis and not the other way around. There are conditions of equivalence of weaker form of Riemann hypothesis with the Lindelof hypothesis, but we will not talk about that. Yeah? I will just try to tell you why how we show that the Lindelof hypothesis how the Riemann hypothesis implies the Lindelof hypothesis. So what we will show is a theorem okay yeah so that log of zeta s is less than log of tau to the power 2 minus 2 sigma plus epsilon for sigma, which is between half and 1, and tau, which is greater than or equal to 2. Yeah. So this is the result that we will prove. So to prove this, we will use the Hadamar's three-circle lemma, which says if I take 3 circles which are concentric, and then we define some maximums and so on. It's easy. It's classical and it's easy, and I won't do it. But we could do it in in one of the tutorials. So this is the theorem we'll use, Hadamard's three-circle lemma. I mean, these are not meant for people who have already worked on the question. They already know how to prove it. But if you have not worked on it, it's a good idea to dirty your hands. Like either you take a chalk and write, and your hands are dirty, or you take a pen and write. And like if you just see something that's done on the board, it always looks very easy. Yeah, it always looks very doable and easy. But then try to do it yourself. Yeah. So, that I leave this as an exercise. We will use Hadamard's three-circle lemma. Yeah. So I take statement is that if I take f of s to be a holomorphic function, on the annulus R1 less than equal to absolute value of s less than equal to R2. So annulus means when I have something like that, I have no, I don't need a annulus doesn't need a I have a circle and I have another circle. They're concentric, and this is the area here. Yeah, that's the annulus. And I let m of r be the maximum value that f of s takes on the circle s equal to r. Okay, then the maximum value of r2, okay, I'll write it. It's a somewhat long line, so I'll write it here. What we are doing now is we are going to prove this theorem. This is the theorem we are going to prove, and that's the lemma that we will use for this. So three circle lemma. So what happens? M of R2 log R.
The function is holomorphic inside the index, but the way you have defined gamma, what is the guarantee that it will be bounded inside the index? Means depend on the angular sum. But the R will like
R2. This R is between R1 and R2. There are three concentric circles.
I mean, we are taking the maximum of modulus of the entire circle.
No, on the annulus. On the here. It's between R1 and R2. Is there a confusion on this? This is less than equal to MR1 log R3 by R2, and MR3 log R2 by R1, which implies that MR2 is less than or equal to MR1 times 1 minus lambda, and MR3 to the power lambda for some lambda between 0 and 1. You know this definition. This is the definition of being log concave. So for any three concentric circles, what are my three concentric circles? R1 less than R2 less than R3. So since I want them really to be different circles, I don't include the equality. So this means really that there is a log concave. Is there a problem? First one is this one. Is there a problem here? R3 by R1. Yeah, R3 by R1, then you have R3, R2, R2, R1. Yeah. Thank you. So, okay. So this you can do as another exercise. Prove this. Okay, it's not difficult. There's nothing difficult in the story. You just have to prove it. Yeah. So this means log concave. Yeah. This last condition means that it's log concave. So now we want to prove. This is what we will use for three circle. So if it's a constructive proof. If we choose well the circles, then you will be able to prove this theorem. So I will assume the Riemann hypothesis, proof of theorem 1. Yeah. So we said that if the Riemann hypothesis is true, then so what happens? So yeah, we will assume the Riemann hypothesis. Yeah, I'm sorry. If the Riemann hypothesis is true, yeah. So assume that the Riemann hypothesis is true. Okay. Now consider the function f, because I will try to construct the circles with this. So f of w, this I just defined to be log of zeta plus zeta S0 plus w divided by zeta S0, yeah, where S0 is equal to 2 plus I gamma. Okay. So what can I say about this function capital F? What we can say about this function capital F is that it is holomorphic so F is, you agree with me that F is holomorphic somewhere, okay? It's holomorphic somewhere. We did not do too many things about the absolute value of zeta. Yeah, so there are nice results. So the 3/2 that I'm writing here is not sacred. You could use something else. It just happens that 3/2 exists. Yeah, so we didn't do many of this the zero free region and of the Riemann zeta function and the bounds in the critical strip we didn't do in much detail. Yeah, so among other things there is the Vinogradov-Korobov theorem, which gives you this. It's probably the best known result. But so this 3/2 that I write here is not particularly, don't be upset about it, because because zeta s can be bounded. Yeah. So this, when omega is less than 3/2. Yeah. So it's not 3/2. If you don't know that it's 3/2, it's not very serious. So now you take some delta, which is between 0 and 1, the real part of f of w is less than equal to big O of log of tau, where omega, this is the same 3 by 2 that I'm using here, is less than equal to 3 by 2 minus delta. So this remark, this follows from bounds on of zeta s, or rather absolute value of zeta s. Okay. So therefore, zeta of s is less than equal to log tau, tau greater than or equal to 2, and sigma greater than or equal to 1 minus c upon log tau. Okay, so let's give this a name. So this one, this follows from what is called the real part lemma in complex analysis. Have you followed some courses in complex analysis? It's also called the Borel-Category lemma, and so but I have to stop. It's an hour. We could continue with this proof in the second part in the afternoon, and then we will see an application of the Lindelof an application of this result. Yeah, it will involve the Mobius function, and we will do that. Yeah, so I should have finished it, but I haven't finished it. Okay, but I have an hour, and I have, I don't know, another 16 hours maybe, yeah, the next week. So I have some time. Yeah. So,
I mean, one today and 15 hours.
16 now. Yeah, 2 today and 15.
One more or 15 hours.
15 plus 2 is 17.
Oh, right. Yeah, but 1 hour is gone.
So 15. So yeah, 15 plus 2 minus 1. Yeah, that's right. So yeah, so I'll stop here. Okay. If you have questions and doubts and so on, we can continue at 3 o'clock today, right?